What is up, amigos? Today we're talking about slipstream aerodynamics, and we'll be going through the drag effects and the lift effects. So first of all, what is slipstreaming? So let's say we have two cars, and I'm just going to draw them as boxes just for idealized purposes. And they are in sequence, so one behind the other, and we have the free stream flow coming in this way. And this car, this is the second car, number two, this is number one, gets close to the first car and gets in the wake of this car. And what effects does this have on the drag of both cars and the lift of both cars? So first of all, let's talk about the drag of car number two, because this is quite obvious, and then we'll go into some a little bit more surprising results for car number one in a second. So first of all, as car number two gets closer to car number one, it goes into its slipstream, so into its wake. And as a result, the drag of car number two drops dramatically. In fact, generally speaking, it's about 30 to 40% drag reduction that this car will experience as it gets very close to car number one. So why is that? So let's think about what the drag of this second car is to begin with. For most cars, really, the major component of drag is pressure drag, and that is when we have a difference in pressure on the upstream face compared to the downstream face. So that change in pressure means that there's a net force, and that results in this drag. So if this second car gets very close to the first car, and let's say this free stream velocity is 20 meters per second, well, that's the free stream velocity. As it goes over the first car, there's now going to be a wake, and this second car is really seeing most of this wake. And in the wake, this velocity might be on average 10 meters per second. So the velocity is much lower. As a result, the flow going over this car is now significantly slower. And that results in there being less of a pressure drag, because there's not nearly as much of a stagnation pressure at the front here, compared to the high pressure at the front here, compared to if there was 20 meters per second flow hitting it. So that results in a lower pressure difference between front and back, which then results in a lower drag, a lower force. So that is fairly well known what the effects of the slipstreaming is on the second car, although the magnitude of about 30-40% drag reduction is maybe not as well known. But what about the first car? What happens to the drag of this car? Well, a little bit surprisingly, this drag also drops, this coefficient, as this second car gets closer and closer. So why is that? I mean, this is upstream, so how does that make sense? It's still seeing the same velocity, but let's think about what's happening with the second car. As the flow goes over the first car and comes down and hits the front of the second car, okay, it's slow moving flow, but this second car is now effectively ramming this air forward. It's not exactly like that, but you can think of it like that. In reality, what is actually happening is you have a high pressure at the front here, and going from the very first molecule of air at the front compared to the second molecule doesn't mean that we just get this all of a sudden a significant drop in pressure. The high pressure that we see gradually dissipates as we go forward. And as this second car reaches this first car, this high pressure zone now starts impacting this first car, sorry. So the back here is actually seeing a higher pressure. So the high pressure at front is sort of cancelling out with the higher pressure at the back, which then results in a net force reduction. And that means that the drag drops. And we get about a 20 to 30% drag reduction here on average for this first car compared to the 30 to 40% drag reduction. So it's not as much, but it is still pretty good. And that is why if you look at, for example, NASCAR, if you see like all these cars in a row in this like train kind of configuration, they just start like surging ahead of single cars or even one or two cars slipstreaming. That's because of this effect happening here. Not only do the second cars and third cars go faster, but the first cars also go faster. And this is also the case in, like, if you look at Tour de France or whatever with the cyclists. What about the lift though? That is the drag. Well, if we look at the second car, the first car is not really that affected that much. The rear axle is kind of a little bit affected. The closer this gets, the less the rear axle will experience a increased lift or downforce. So if this rear axle here is producing lift, this car coming closer will reduce that lift. It is producing downforce. This rear car coming forward will reduce that downforce as well. So it'll tend towards zero. But the second car, what we see here is we have two axles with regular cars. And as this second car gets close to the first car, let's think about what's happening here. So again, we have the flow coming over the first car and it hits this second car. It's the wake. It's, let's say, 10 meters per second on average. So this car now is seeing a much slower moving fluid, and not only will all these flow control devices that you have on this car be affected and negatively, but also the car itself can't really produce as much lift or as much downforce as it would usually, because it has less energy to work with in the fluid. The fluid is slower moving, so we can't really take as much energy out and produce lift and downforce out of it. So that results in the downforce or the I'm going to say downforce instead of D to not confuse with drag, but either the lift produced or the downforce produced tend towards zero. So we'll get a reduction in both of these, 10, 20, 30%, depending on how close we get to this first car. That is the front axle, and that is mostly affected by the wake. The rear axle is also affected in the same kind of sense, but not as much. So you need to get quite close to the front car in order for the rear axle to start experiencing these negative effects severely. But again, the same idea holds where, okay, that you have slow moving flow going over the car, which means that the rear of the car can't really produce as much lift or downforce because there's not as much energy in the flow to take advantage of. As a result, the lift and downforce, whatever you're producing, tend towards zero. So that is how the slipstream of these two cars affect the drag of each car and the lift of each drag. And if you like this video, make sure to like, click the subscribe button, and I'll see you. Peace and amigos.